Tonight, we're going to talk about the planet that started exactly like Earth. Same size, same age, same raw materials, same neighborhood in the solar system. One of them became a world covered in oceans, wrapped in a breathable atmosphere, teeming with life. The other became Venus. A planet where the average surface temperature sits above the melting point of lead. The clouds are made of concentrated sulfuric acid. And every probe we've ever sent to the surface lasted less than 2 hours before the environment destroyed it. 2 planets. Same starting conditions. Completely different outcomes. And by the end of tonight, you're going to understand why Venus is the deadliest planet in the solar system, and how it ended up this way, starting from the exact same place we did. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you probably already know about Venus, or think you know. Venus is the second planet from the Sun. It's the brightest natural object in our sky after the Sun and the Moon. Mesopotamian astronomers tracked its movements with systematic precision, going back at least 5,000 years, when it would appear as the morning star, when as the evening star, and how long it would disappear between. The Mayans built entire astronomical calendars around Venus's 8-year cycle, with predictions accurate to within a day across centuries. The Greeks named it Phosphorus before dawn and Hesperus at dusk, not realizing until around the 6th century, before the Common Era, that both were the same object. The Romans folded it into a single name, Venus, after their goddess of love and beauty. For all of recorded human history, this planet has been associated with something luminous and beautiful, something that inspired myth and calendar and poetry across every civilization that ever existed under an open sky. And from a distance, through any telescope, from any observatory, from any spacecraft looking back before atmospheric entry, it still looks exactly that way. A smooth, featureless, white-yellow orb wrapped in thick, reflective cloud. Serene. Almost peaceful. That image is completely misleading. The clouds aren't water vapor. They aren't ice crystals. They're sulfuric acid. And they're just the outermost layer of what makes Venus the planet it is. Venus sits about 67 million miles from the Sun, on average. Earth sits about 93 million miles out. That gap might seem like explanation enough. Venus is closer to the Sun, so of course it's hotter. But the numbers don't support that simple explanation. Mercury sits about 36 million miles from the Sun. Venus is almost twice as far from the Sun as Mercury is. At Mercury's distance, the Sun-facing side reaches about 800 degrees Fahrenheit, or 427 degrees Celsius, during its long day. Venus reaches about 900 degrees Fahrenheit, or 482 degrees Celsius, 10% hotter than Mercury, despite being nearly twice as far away. And the distribution of that heat is radically different from Mercury's. Mercury's night side plunges to around negative 290 degrees Fahrenheit, or negative 179 degrees Celsius. The day side is scorching, the night side is frigid. Mercury's global average surface temperature works out to around 332 degrees Fahrenheit, or 167 degrees Celsius. Venus's global average surface temperature is around 900 degrees Fahrenheit, or 482 degrees Celsius, nearly 3 times Mercury's average. The poles of Venus are nearly as hot as the equator. The night side of Venus is nearly as hot as the day side. The highest mountains on Venus are only somewhat cooler than the lowland plains. The planet is uniformly, relentlessly, completely heated. Mercury fluctuates wildly because it has no atmosphere to trap heat and redistribute it. Venus doesn't fluctuate because its atmosphere traps everything. Understanding that atmosphere, what it's made of, why it works the way it does, and how it got that way, is the key to understanding everything about Venus. The atmosphere of Venus is about 96% carbon dioxide. The remaining 4% is mostly nitrogen, with trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon mixed in. Water vapor is present at roughly 20 to 30 parts per million in the lower atmosphere. That's essentially nothing. A trace. A ghost of what may once have been far more. 96% carbon dioxide at 92 times Earth's atmospheric pressure. Carbon dioxide is a greenhouse gas. It absorbs infrared radiation, thermal energy, and prevents it from escaping into space. Earth has carbon dioxide in its atmosphere at about 0.04% of the total composition. That fraction is 400 parts per million. Small, but real. And that small fraction contributes meaningfully to warming our planet. Without any greenhouse effect at all, Earth's average surface temperature would be approximately 0 degrees Fahrenheit, or negative 18 degrees Celsius. Frozen. With the greenhouse effect from our current mixture of CO2, water vapor, methane, and other trace gases, Earth averages around 59 degrees Fahrenheit, or 15 degrees Celsius. The greenhouse effect adds nearly 60 degrees to Earth's average temperature. It's the reason Earth has liquid water. It's the reason we exist. Now imagine that same mechanism running not on trace amounts of greenhouse gas, but on an atmosphere that is 96%, one of the most effective heat-trapping gases known, compressed to 92 times Earth's atmospheric pressure. The mechanism is the same. The scale is completely different. Sunlight arrives at Venus. A large fraction bounces straight back into space. Venus's cloud layers are highly reflective, returning about 65% of all incoming sunlight directly to space. The remaining 35% makes it through the upper atmosphere and cloud layers and reaches the lower atmosphere and surface. The surface absorbs that energy and radiates it back upward as infrared radiation as heat. The CO2 absorbs that infrared. It re-radiates some of it downward. The surface absorbs it again, radiates again. The CO2 absorbs again. Every thermal photon entering that cycle bounces back and forth between the surface and the dense lower atmosphere many times before eventually escaping to space. The system has been running this way for hundreds of millions, possibly billions of years. The equilibrium it reached is 900 degrees Fahrenheit. That's the temperature where enough heat is finally escaping through the dense atmosphere to balance the incoming solar energy. 900 degrees. Permanently. Everywhere. All the time. 900 degrees Fahrenheit, or 482 degrees Celsius, is a number that needs to be anchored in something physical to be understood. Lead melts at 621 degrees Fahrenheit, or 327 degrees Celsius. Lead is liquid on the surface of Venus. Not just warm, not just soft. Liquid. If you could somehow pour molten lead onto Venus's surface, it would actually cool over time, and eventually solidify not because Venus is cool enough to solidify lead by Earth standards, but because the molten lead starts out even hotter than 900 degrees when fully liquid, and at 900 degrees it's below the melting point, so it would eventually crystallize. But any solid lead object arriving at Venus's surface from Earth would melt within moments of exposure. Zinc melts at about 787 degrees Fahrenheit, or 420 degrees Celsius. Zinc is liquid on Venus's surface. Tin melts at around 449 degrees Fahrenheit, or 232 degrees Celsius. Any tin object would melt long before a spacecraft carrying it could even complete its descent. Aluminum melts at around 1,220 degrees Fahrenheit, or 660 degrees Celsius. Aluminum survives Venus's surface temperature without melting, but at 900 degrees, it's at about 75% of its melting point. At that temperature fraction, aluminum loses most of its mechanical strength. It becomes soft and deformable. Any aluminum structure would slowly sag and fail under its own weight. Steel alloys have higher melting points, generally over 2,300 degrees Fahrenheit, or roughly 1,260 degrees Celsius. But steel loses significant structural strength at temperatures in the 800 to 900 degree range. Steel structures at Venus's surface temperatures would have a fraction of their room temperature strength. The rocks themselves are fine. Basalt and silicate minerals melt at temperatures generally above 2,000 degrees Fahrenheit, or about 1,090 degrees Celsius. The landscape is solid, but every common engineering material we use to build machines, every metal, every conventional polymer, every standard electronic component behaves poorly or fails completely at Venus's surface temperature. This isn't just a problem for unprotected objects. It's the fundamental engineering problem that has limited every Venus surface mission in history and continues to limit them today. Insulation slows heat transfer. It doesn't stop it. At Venus's temperature differential, roughly 850 degrees Fahrenheit above the operating range of most electronics, even the best thermal insulation buys you time. Not indefinitely. The heat gets through. Always. And when it does, every machine that arrived at Venus stops working. Every time. Before we get to the probes that tested all of this directly, we need to add pressure to the picture, because the pressure on Venus's surface would be catastrophic long before the heat fully manifested. The atmospheric pressure on Venus's surface is approximately 92 times the atmospheric pressure at Earth's sea level. Earth's sea level pressure is about 14.7 pounds per square inch. Venus's surface pressure is around 1,350 pounds per square inch. To experience comparable pressure on Earth, you'd need to descend to approximately 3,000 feet beneath the ocean's surface. Not to the Mariana Trench, nearly 7 miles deep, just about 3,000 feet, a third of a mile down. 1 dar. That pressure is what exists on Venus's surface everywhere, in the flattest lowlands and on the slopes of the highest volcanoes, at the equator and at the poles, in every corner of the planet, always. For human biology, this pressure would be fatal, with essentially no delay. Every biological process that depends on pressure equilibrium would fail simultaneously. The lungs cannot expand against that external pressure. The cardiovascular system cannot maintain circulation against it. Gases dissolved in blood and tissue would behave abnormally. And this is before accounting for the temperature, which would kill by different mechanisms simultaneously. There is no technology, no suit, No armor, no device that a human could wear today and survive on Venus's surface. Not because we haven't designed carefully enough. Because the combination of heat and pressure, in combination with the corrosive atmospheric chemistry, creates a set of simultaneous requirements that no current materials or engineering approach can satisfy together. For machines, pressure is more tractable. Pressure vessels can be built to withstand 92 atmospheres. Deep-sea submersibles operate at comparable pressures. The problem is combining that pressure vessel with thermal insulation, with scientific instruments, with power systems, with communication systems, with structural integrity at high temperature, while keeping the total mass low enough to actually deliver to Venus's surface intact. Every additional element of survivability adds mass. Every gram of thermal protection takes mass away from payload. Every backup system adds complexity and potential failure modes. The engineering trade-offs are genuinely brutal. And after more than 2 decades of refined Soviet engineering across more than 15 spacecraft, the best survival time achieved on Venus's surface was 127 minutes. 2 hours and 7 minutes. Then the environment always won. The Soviet Union built the most ambitious planetary exploration program directed at a single target in history. The Venera program spanned from 1961 to 1983. It required 22 years. More than 15 spacecraft. Complete redesigns of the mission architecture multiple times. And it produced the only data we have from Venus's surface to this day. The early missions were destroyed before they could tell us much. Venera 1 launched in February of 1961 and lost contact before reaching Venus. No data. Venera 2 flew past Venus in February of 1966. Lost contact before any atmospheric measurements. Venera 3, launched in the same batch as Venera 2, became the first spacecraft to reach the surface of another planet when it impacted Venus in March of 1966. No transmission survived. But the trajectory and impact confirmed that reaching Venus was physically possible. The targeting worked. The problem was surviving the journey through the atmosphere and the surface conditions themselves. Venera 4 was a major milestone. It launched in June of 1967 and arrived in October of the same year. It was designed to enter the atmosphere and descend on a parachute, transmitting data on the way down. And it did exactly that. As Venera 4 descended, it transmitted temperature and pressure readings directly to Earth. The atmosphere was confirmed as more than 90% carbon dioxide. The temperature at altitude was over 500 degrees Fahrenheit, or 260 degrees Celsius. The probe stopped transmitting before reaching what engineers believed was the surface. Initial reports said it had reached the surface and been destroyed there. Further analysis revealed something more troubling. The probe had been crushed by atmospheric pressure at an altitude of about 15 miles. At that altitude, the pressure was around 18 to 20 atmospheres. The probe was theoretically rated to 22 atmospheres. It failed before reaching a pressure it was supposed to survive. The reason was simple and alarming. The models of Venus's atmosphere that Soviet engineers had been working from were wrong. Seriously, wrong. The atmospheric pressure increased with depth far faster than the models had predicted. The surface pressure was dramatically higher than any calculation had suggested. Venera 4's destruction proved that everything built before that moment was too weak. The entire spacecraft design would need to be reconsidered from scratch. Venera 5 and Venera 6 arrived in May of 1969. Both were redesigned to survive higher pressures. Both entered Venus's atmosphere. Both transmitted data during descent. Both were eventually crushed before reaching the surface. The surface pressure was confirmed to be extraordinary, far beyond what the probes could handle. Engineers now had to figure out exactly how high the pressure was and build something that could take it. The answer they came up with was Venera 7. Venera 7 launched in August of 1970. It was built around a pressure vessel rated to 180 atmospheres, nearly twice the expected surface pressure, with a substantial safety margin. The thermal insulation was significantly upgraded over previous designs. The parachute system was modified to allow faster descent through the hottest layers of the atmosphere, reducing the total time exposed to the worst conditions. Everything about the design was oriented toward one goal: survive long enough to reach the surface and transmit data. On December 15, 1970, Venera 7 entered Venus's atmosphere. It descended. It survived the crushing pressure buildup through the clouds. It survived the lower atmosphere. The surface arrived. And for 23 minutes, Venera 7 transmitted data from the surface of another planet. The first transmission from the surface of another world in history. 23 minutes. The surface temperature was approximately 880 degrees Fahrenheit, or 471 degrees Celsius. The surface pressure was confirmed at about 90 atmospheres. Then Venera 7 went silent. The environment had won again, but not before it gave us those 23 minutes of data. The Soviet mission controllers celebrated. After 9 years and multiple failed attempts and complete redesigns, they had achieved something that had never been done. Data from the surface of another planet. And they'd done it in the most hostile environment in the solar system. Venera 8 followed in July of 1972 and survived about 50 minutes on the surface. It measured light levels and confirmed that despite the thick cloud cover above, enough sunlight was reaching Venus's surface to make photography possible. About 0.5% of the incoming sunlight made it through. Dim by Earth standards, but sufficient. That finding was critical for planning what came next. Venera 9 and Venera 10 arrived in October of 1975. These were the first missions to include cameras designed to photograph the surface. Both survived long enough to send images. What did Venus look like? Angular, jagged rocks. Not the smooth, rounded stones of a riverbed. Not the worn, eroded surfaces of an ancient landscape shaped by water. Sharp-edged, fractured, angular basalt slabs looking freshly erupted. Looking like rocks that had never been touched by water. And geologists understood immediately what that meant. No water had shaped those rocks. Not in recent geological time. Maybe not ever. The landscape was geologically fresh and geologically static. Erupted onto the surface at some point. Sitting there unchanged since. Because nothing had the power to change it. No rain to erode it. No rivers to transport it. No life to break it down. Just rock and heat and silence. Venera 11 and Venera 12 arrived in December of 1978 and detected something unexpected during their descents. Lightning. Electrical discharges in Venus's atmosphere, detected through radio emissions, This was the first evidence that Venus generates lightning, a subject still being studied and debated today. The nature of Venus lightning is different from Earth's on Earth. Lightning requires water droplets and ice crystals colliding in storm clouds, processes that drive electrical charge separation. Venus has no water clouds. The mechanism for Venus lightning is thought to involve sulfuric acid droplets, volcanic ash, and possibly other charged aerosol particles in the cloud layers. The debate over whether what the Venera probes detected was truly lightning or some other phenomenon is still ongoing. But the electrical activity is real. And then came Venera 13. Venera 13 arrived in March of 1982. It was the most sophisticated Soviet Venus lander yet, and it set a record that has never been broken. 127 minutes on the surface of Venus. 2 hours and 7 minutes. Transmitting continuously throughout. And it sent back color photographs. The images showed orange-brown basalt slabs covering the ground, some soil material between the rocks. The horizon in every direction was flat and rocky. The sky, what could be seen as the light source, was orange, reddish amber, like looking at the world through ancient amber glass. Everything bathed in that color. The photos look almost ordinary. Just rocks on ground under an orange sky. Ordinary, until you remember what surrounded that camera. 900 degrees radiating from every surface. 90 atmospheres pressing from every direction. Sulfuric acid clouds above. And the certain knowledge that in minutes, the machine taking those photographs would be gone. Not through any failure of engineering. Through the simple, inevitable victory of the environment over anything we'd brought to it. Venera 13's cameras captured something important beyond just the rocks. The surface material was analyzed by drilling and chemical testing. The results matched terrestrial basalt with some differences. Volcanic rock, the kind that erupts from volcanoes, confirming that Venus's surface is geologically volcanic in origin, as radar from orbit had suggested. After Venera 13 and Venera 14, which arrived days later and survived about 57 minutes, the Soviet Venera program shifted to orbital missions. Venera 15 and Venera 16 arrived in late 1983 as radar mapping orbiters. They began the first systematic radar mapping of Venus's surface, revealing the broad geological features, the highland regions, the volcanic plains, the coronae, the tesserae, and the distribution of impact craters. The lander missions were done. The program that had started in 1961 failed repeatedly, redesigned completely multiple times, and eventually succeeded beyond the expectations of anyone who'd watched the early failures. That program was finished. Its legacy is every surface image and chemistry measurement of Venus we've ever had. Every single piece of data from Venus's surface comes from those probes. No one has sent a surface mission to Venus since Venera 13 and Venera 14 in 1982 and 1983. That's over 40 years. No new surface data. Because we haven't solved the engineering problem. We still don't have a spacecraft that can survive Venus's surface for more than a few hours. We're still working on it. Understanding what Venus's surface environment actually is like. Not just the temperature and pressure numbers, but the lived physical reality of the place, requires going through every aspect of it carefully. Start from the outside. Venus's clouds sit between about 28 miles and 43 miles above the surface. 3 distinct cloud layers, each with slightly different properties and acid concentrations. The upper cloud layer, from roughly 40 to 43 miles, has smaller sulfuric acid droplets at concentrations of about 75% sulfuric acid by mass. The middle cloud layer, from about 35 to 40 miles, has larger droplets and slightly higher acid concentrations. The lower cloud layer, from about 28 to 35 miles, contains even larger droplets, some of which are large enough to fall as droplets as rain, in a sense. But this rain never reaches the surface. The temperature in the lower atmosphere is so high that the droplets evaporate before they travel far. The sulfur compounds rise back up, rejoin the cloud system. The acid cycle continues. Below 28 miles, the atmosphere is relatively clear. Not blue sky clear, not transparent, but clear of clouds. The atmosphere below the clouds is still extremely dense and acts as a scattering medium. Light doesn't travel in straight lines the way it does in clear air. It scatters, bounces around, fills every direction equally. There are no shadows on Venus's surface. Everything is uniformly illuminated by light coming from all directions in the sky at once. The horizon is strange. Venus's dense atmosphere bends light significantly more than Earth's air does. Atmospheric refraction, the bending of light as it passes through media of different densities, is minor on Earth. It causes the slightly squashed appearance of the setting sun. It makes stars twinkle. On Venus, the effect is so extreme that your line of sight literally follows the curve of the planet. Standing on Venus's surface and looking out toward the horizon, you wouldn't see the ground curving away from you as it does on Earth. The horizon wouldn't drop. The atmosphere would bend your line of sight downward to follow the surface, and the surface would appear to curve upward in every direction. You'd look like you were standing in the bottom of a shallow bowl, with the land rising gently toward a curved horizon in every direction. Orange light coming from above, the ground curving upward all around you. 900 degrees of heat radiating from every rock and every grain of soil within reach. 92 atmospheres pressing from every direction. Sulfuric acid clouds, completely invisible above you, dissolved into a general orange glow by the intervening atmosphere. This is Venus's surface. The physical experience of it. Not dramatic. Not dynamic. Not even particularly striking visually. Just utterly hostile. In every direction, at every moment, without pause. The wind at Venus's surface is worth examining carefully because it surprises most people. Surface wind speeds on Venus are relatively gentle. 2 to 4 miles per hour. That sounds like nothing. On Earth, that would barely move a leaf. You'd barely notice a 2 to 4 mile per hour breeze. But recall, Venus's atmosphere at the surface is 92 times denser than Earth's air. The force a moving fluid exerts depends on its density. The same wind speed in a much denser medium carries far more force. Ocean currents move at speeds that might feel like a slow walk in air. But standing in a waist-deep ocean current of even 2 to 3 miles per hour is genuinely difficult. Water is about 1,000 times denser than air. You can barely walk against even a modest water current. Venus's atmosphere at the surface is 92 times denser than Earth's air. Not as dense as water, but far denser than anything you'd experience walking through air on Earth. A 2 to 4 mile per hour wind in Venus's surface atmosphere exerts real, noticeable force. Not enough to knock you over, but enough to push you consistently. Enough to make movement feel effortful. Enough that you'd be aware of it constantly. And this is the calm. The bottom of the atmospheric column, where the densest, slowest moving air sits. Go up through the atmosphere, and the story changes completely. At the cloud layers, starting around 28 miles up, the winds are much stronger. The lower cloud layer has winds of around 20 to 30 miles per hour. The middle and upper cloud layers have winds of up to 200 miles per hour. At the very top of the cloud deck, around 40 to 43 miles altitude, the winds are circling the entire planet at over 200 miles per hour. Sustained. Constant. Global. One complete circuit of Venus takes about 4 Earth days at the cloud tops. Venus's own rotation takes 243 Earth days. The atmosphere moves 60 times faster than the planet beneath it. This is called superrotation, and it's one of the most extreme atmospheric phenomena in the solar system. No other planet has atmospheric superrotation anything like this. On Earth, the fastest jet stream winds blow around 200 to 250 miles per hour, but they're localized, variable, and seasonal. They shift position by hundreds of miles. They slow down and speed up with the seasons. Venus's superrotating cloud layer is global, permanent, and relentless. It has been blowing at those speeds continuously for longer than any human civilization has existed. Probably for longer than our species has existed. Possibly for millions of years. Understanding why is one of the genuinely unsolved problems in planetary science. The leading models invoke thermal tides, the rhythmic heating of different parts of the atmosphere as they rotate through sunlight and shadow, combined with angular momentum exchange between the sunlight, surface, and the atmosphere. But a complete quantitative explanation that matches the observations doesn't exist yet. Venus's atmosphere is doing something extreme that we can measure precisely and can't fully explain. The sulfuric acid clouds are more than just a chemical hazard. They're the active engine of Venus's atmospheric chemistry. Sulfuric acid forms in Venus's upper atmosphere through a specific set of reactions. Sulfur dioxide, a volcanic gas, rises from the surface into the upper atmosphere. There, ultraviolet radiation from the sun drives reactions that combine sulfur dioxide with water vapor and oxygen to form sulfur trioxide and eventually sulfuric acid. The sulfuric acid condenses into droplets. The droplets form clouds. Eventually, the droplets grow heavy enough to fall as precipitation acid rain through the cloud deck. But as they fall through the increasingly hot lower atmosphere, they evaporate. The sulfuric acid breaks back down. The sulfur dioxide returns to the lower atmosphere, rises again, reacts again. The cycle is continuous, and it's powered by ongoing volcanic activity. Venus is geologically active. Volcanoes pump sulfur dioxide into the atmosphere continuously. This replenishes the supply of sulfur for the acid cycle. Without active volcanism, the sulfur would gradually be absorbed by surface rocks and the cloud layers would thin. The fact that they remain thick suggests active geology continues to supply the sulfur. The concentrations of sulfuric acid in Venus's clouds range from about 75 to 96% pure acid by mass, depending on altitude and temperature. For reference, car battery acid is typically about 30 to 40% sulfuric acid. The concentrated acid used in industrial processes, the kind used to make fertilizers, metals, and chemicals, is typically 98%. Venus's clouds are approaching that industrial concentration. On contact with any metal surface, that acid reacts aggressively. It dissolves zinc almost immediately. It attacks iron and steel over longer periods. It reacts with most aluminum alloys. Even titanium, one of the most acid-resistant engineering metals, is attacked by concentrated sulfuric acid at elevated temperatures. Any spacecraft transiting Venus's cloud layers is being chemically attacked from outside the entire time it descends. The Venera probes were designed to survive that transit, and they mostly did survive it. But the acid transit added to the thermal load and the chemical degradation of every exposed surface, contributing to the cumulative failure that eventually ended every mission. The acid doesn't just corrode. It changes the composition of the surfaces it contacts. It introduces sulfur compounds into metal surfaces. It alters the physical properties of materials, making them more brittle, less thermally conductive, less structurally sound. Everything that passes through Venus's clouds arrives at the surface already somewhat compromised, already partly consumed by the chemistry of the journey. The question of what Venus looks like from orbit, from above the clouds, brings us to the Magellan spacecraft. Magellan launched in May of 1989. It arrived at Venus in August of 1990. It carried a synthetic aperture radar instrument that could map Venus's surface through the cloud cover. Radar waves penetrate the clouds completely. They bounce off the surface and return to the spacecraft. By carefully analyzing the return signals, the spacecraft's instruments could build detailed images of Venus's surface as if there were no atmosphere at all. Over 4 years, Magellan mapped roughly 98% of Venus's surface. The resulting maps showed everything. The vast volcanic plains covering about 80% of the surface. The highland region's Ishtar Terra in the north, roughly the size of the continental United States, and Aphrodite Terra near the equator, larger than Africa. The Maxwell Montes mountain range at the eastern edge of Ishtar Terra, rising about 7 miles above the surrounding plains, slightly higher than Mount Everest. At the peaks of Maxwell Montes, the temperatures drop to around 450 degrees Fahrenheit, or 232 degrees Celsius, cooler than the lowland plains, but still searingly hot. At those higher altitudes, Magellan's radar revealed something unexpected. The highest peaks had high radar reflectivity. They were highly reflective to radar waves. The explanation most scientists favor is a metallic frost, not water, ice. At 450 degrees Fahrenheit, or 232 degrees Celsius, water ice is impossible. Instead, certain metallic compounds, possibly tellurium compounds, iron pyrite, or bismuth-bearing minerals that are volatile at lower altitude temperatures, apparently evaporate there, rise in the atmosphere, and then condense onto the cooler, high-altitude surfaces. The highest peaks of Venus are dusted with something metallic, a mineral frost that wouldn't look like snow, darker, perhaps iridescent, sitting on the rocks the way frost sits on Earth's mountaintops, but made of metal compounds instead of ice. Magellan also revealed the tesserae. Tessera terrain, named after the Latin word for tiles, consists of regions of highly deformed, ancient-looking crust, intersecting ridges and valleys, running in multiple directions. A chaotic, crumpled appearance, as if the surface had been compressed and deformed multiple times from different directions. Tesserae don't look like any other terrain type on Venus. They look old, worked over, ancient. And geologically, they probably are. The leading interpretation is that tesserae represent the oldest exposed crust on Venus material that survived whatever catastrophic event reset most of the planet's surface several hundred million years ago. They may contain a record of Venus's earlier history, before the runaway greenhouse completed its work, before the oceans, if they existed, were destroyed. Magellan also mapped Venus's impact craters. About 970 of them, randomly distributed across the surface. This distribution is deeply informative. A planet that has been geologically active for its entire 4.5 billion year history, but has plate tectonic recycling, would gradually erase old craters as new surface forms. A planet that has been geologically stable for most of its history would accumulate craters in large numbers the way the Moon has. Venus has relatively few craters, and they're distributed randomly across the surface in a way that suggests the entire surface was reset at roughly the same time in the relatively recent geological past. Recent, in geological terms, means within the last few 100 million years, probably between 300 and 500 million years ago. Everything before that, reset, is buried. What we see now has formed since. The geological interpretation of Venus's surface centers on a concept called the stagnant lid. Earth has plate tectonics. The outer rocky shell, the lithosphere, is broken into a mosaic of large plates that move slowly, driven by convection currents in the mantle below. Where plates collide, mountains rise. Where they separate, new seafloor forms. Where one dives beneath another, old surface is recycled into the mantle. This continuous recycling distributes heat from the interior, moderates volcanic activity, drives the carbonate-silicate cycle, and renews the surface over geological time. Earth's oldest surface rocks are about 4 billion years old, but most of the seafloor is less than 200 million years old, constantly recycled by subduction. Venus doesn't appear to have this kind of global plate system. The surface doesn't show the same kind of organized plate boundaries. The long chains of volcanoes, the linear mountain belts, the deep ocean trenches that on Earth mark plate edges. Instead, Venus's lithosphere appears to be a single, mostly rigid plate covering the whole planet. A stagnant lid. Heat from the mantle builds up beneath this rigid shell. It can't escape efficiently through the kind of continuous convective recycling that plate tectonics provides. Instead, it accumulates. Over hundreds of millions of years, the buildup of heat weakens the lithosphere from below. Eventually, the lid can't hold. It breaks catastrophically. Mantle material surges to the surface in massive volcanic events. The entire surface is flooded with lava. Everything is buried. The geological record is reset. And then a new rigid lid forms and the cycle begins again. This is the stagnant lid model with catastrophic resurfacing. The impact crater distribution on Venus is consistent with this. Everything reset several 100 million years ago. The craters we see today are those accumulated since the reset. If this model is correct, Venus is currently in the build-up phase. Heat accumulating beneath the lid. Geological tension building. The next catastrophic resurfacing event is somewhere in the geological future. Nobody knows when. Could be tens of millions of years away. Could be sooner. The Veritas and Envision missions will look for signs of current geological stress, deformation, recent volcanism, seismic-like features that might tell us where Venus is in its cycle. If Venus is approaching another catastrophic overturn, that would be one of the most significant findings in planetary science history. The most intriguing discovery related to Venus's current geological activity came in 2023. Researchers reanalyzed radar data from the Magellan spacecraft data collected in 1991 and found something they hadn't seen before. One volcanic feature, a vent on the flanks of Mont Mons, appeared to have changed shape between two radar observation passes taken about 8 months apart. The vent, originally roughly circular, appeared to have expanded and changed shape. The change was consistent with volcanic eruption or magma movement during those 8 months. Not a subtle difference that could be explained by noise in the data. A clear, physical change in the shape of a geological feature on Venus's surface. This was the first direct observational evidence that Venus has active volcanism right now. Not ancient eruptions. Not eruptions from hundreds of millions of years ago. Recent activity, possibly ongoing, which means that the sulfur dioxide being pumped into Venus's atmosphere, driving the acid cloud cycle, is coming from currently active volcanoes. The planet is still building its own poison atmosphere, still replenishing the clouds, still operating the chemistry. The Venera probes didn't just visit a static, dead world. They visited a geologically active one. The acid rain that doesn't quite reach the surface is connected to eruptions still happening on the plains below. The clouds that destroyed parts of every probe come from volcanoes that are still erupting. Venus is alive geologically. It just isn't hospitable. To understand how Venus got this way, you have to go to the beginning. About 4.5 billion years ago, the solar system was newly formed. The sun had just ignited. A spinning disk of gas and dust surrounding it was in the process of assembling into planets. Rocky planetesimals were forming from the dust, small solid bodies a few miles to a few hundred miles across, colliding and merging and growing. Over tens of millions of years, a few larger bodies swept up most of the material in their orbital neighborhoods. In the inner solar system, 4 rocky planets emerged: Mercury, Venus, Earth, and Mars. All 4 formed from fundamentally similar material. The same silicate minerals. The same iron. The same mix of volatile compounds, water, carbon dioxide, nitrogen, sulfur, incorporated from the early solar system. Venus and Earth, forming at comparable distances from the Sun, received similar doses of everything. Similar mass. Similar composition. Similar inventory of water and carbon dioxide and nitrogen. They started the same. The early Venus almost certainly had water. The deuterium to hydrogen ratio in Venus's current atmosphere, about 150 times higher than Earth's, is a chemical fingerprint of water loss. When water molecules escape a planet's atmosphere, lighter hydrogen escapes more efficiently than heavier deuterium. The more water a planet loses, the more enriched in deuterium the remaining hydrogen becomes. Venus's extremely high deuterium enrichment tells us It once had far more water than it does today, possibly as much as an entire ocean's worth. Some climate models support the idea that early Venus may have been genuinely habitable. A dimmer early sun, Venus's slow rotation generating persistent cloud cover on the day side that reflected excess sunlight, and the presence of liquid water, all creating conditions where surface temperatures could have remained in a livable range. Under those conditions, liquid oceans could have existed on Venus for as much as 2 billion years longer than complex life has existed on Earth. Other models are more skeptical, placing Venus at or just beyond the critical threshold even in the early solar system. The honest answer is that we don't know. The evidence either way is incomplete. But the deuterium enrichment tells us water was there in substantial amounts and was lost. The question of when and through what mechanism is still being refined. At some point, the balance broke. The Sun has been slowly increasing in luminosity over its 4.5 billion year lifetime. All stars do this. As they fuse hydrogen in their cores, the core contracts slightly. As hydrogen is converted to helium, the temperature rises. The luminosity increases. Early in its history, the Sun was about 70% as bright as today. Over time, it brightened. As it brightened, the amount of energy arriving at Venus increased. At some threshold, a critical temperature where the rate of water evaporation began to exceed the rate at which the planet could deal with the resulting water vapor in the atmosphere, a feedback loop engaged. Water vapor is a greenhouse gas. More water vapor in the atmosphere trapped more heat. More heat drove more evaporation. More water vapor, more heat. The loop tightened. This is the runaway greenhouse effect. It's not a warming trend that might eventually level off. It's a self-reinforcing cascade with no natural off switch once it begins. The oceans shrank, evaporated. The atmosphere filled with water vapor. And in the upper atmosphere, ultraviolet radiation from the sun was breaking apart water molecules. Photodissociation. Ultraviolet photons carrying enough energy to split H2O into hydrogen and oxygen. The hydrogen, lightweight and moving fast, escaped to space. Especially on Venus, where the weak or absent magnetic field left the upper atmosphere exposed to the solar wind, which carried away the lighter hydrogen atoms efficiently. The oxygen remained. It combined with surface rocks. The water was chemically disassembled, not evaporated, somewhere waiting to fall back, not frozen, somewhere cold, split apart at the molecular level, with the components sent to opposite fates, one into space, one into rock. The water was gone. And with it went the mechanism that might have stopped what came next. The carbon-silicate cycle is one of the most important concepts in understanding planetary habitability. On Earth, it operates like a thermostat. Here's how it works. Atmospheric CO2 dissolves in rainwater to form carbonic acid, a weak acid. That acid falls on exposed silicate rock and slowly weathers it, reacting chemically, dissolving minerals, releasing ions. The weathering reaction pulls CO2 out of the atmosphere and incorporates it into dissolved carbonate minerals. Rivers carry those minerals to the ocean. Marine organisms, shells, coral, microscopic plankton incorporate the carbonates into their structures. When they perish, their shells accumulate on the sea floor and eventually become sedimentary rock. Plate tectonics subducts that rock into the mantle. One plate dives beneath another, carrying the carbon-bearing sediments deep into the earth. In the mantle, at high temperatures and pressures, the carbon-bearing minerals react and eventually release CO2. That CO2 makes its way to the surface through volcanism, erupting from volcanoes as part of the volcanic gas mixture. The whole cycle takes roughly 100,000 to 1,000,000 years for a given carbon atom to complete. And it acts as a thermostat because weathering rates depend on temperature. When the planet warms, weathering rates increase, pulling more CO2 from the atmosphere, cooling things back down. When the planet cools, weathering slows, allowing CO2 to build up from volcanism until temperatures rise again. Earth has maintained liquid water for roughly 4 billion years, despite the sun getting 30% brighter, despite massive volcanic events, despite multiple ice ages, despite asteroid impact. The carbon silicate thermostat is a significant part of why. It adjusts. It compensates. It keeps the planet within the window where liquid water persists. Venus lost this thermostat when it lost its water. Without liquid water, there is no rainfall. Without rainfall, there is no carbonic acid. Without carbonic acid, there is no silicate weathering. Without weathering, there is no carbon drawdown. Volcanism continues pumping CO2 into the atmosphere. Nothing removes it. The CO2 accumulates. More greenhouse warming. More CO2. From volcanism. Nothing to stop it. The new equilibrium, the point where enough heat finally escapes through the dense atmosphere to balance incoming solar energy, is 900 degrees Fahrenheit. That's where the system stabilized. At 92 atmospheres. At 96% CO2. The thermostat didn't fail. The thermostat was destroyed, along with everything that allowed it to function. And once it was gone, there was no way to restore it. Water couldn't return because the temperatures were too high for it to condense. The geology couldn't re-engage the carbon cycle because there was no water. The planet was locked into its new state. Permanently. Venus rotates backwards. Every other planet in the solar system, with the exception of Uranus, which is effectively tipped on its side, rotates counterclockwise when viewed from above the Sun's north pole. Earth, Mars, Jupiter, Saturn, Neptune, counterclockwise. Mercury rotates slowly, but counterclockwise. Venus rotates clockwise. The Sun rises in the west and sets in the east on Venus. And it rotates with agonizing slowness. One full rotation takes 243 Earth days. Venus's orbital period, the time to complete one full circuit around the Sun, is 225 Earth days. The day is longer than the year. The solar day, the actual time between successive solar noons, accounting for the interaction between Venus's retrograde rotation and its orbital motion, is approximately 117 Earth days. More than 3.5 Earth months from one noon to the next. The Sun creeps across the sky so slowly you'd have to watch it for hours to notice any movement. From west to east. Moving backward compared to every other inner planet. The most widely accepted explanation is a giant impact in Venus's early history. Something large, possibly Mars-sized or larger, struck the early Venus at the right angle with enough force to reverse its rotation. Giant impacts were common in the early solar system. The impact that formed Earth's moon was one. The impact that knocked Uranus onto its side was another. The early solar system was a chaotic, violent place, full of large objects on unstable orbits. Venus took a hit that flipped its spin. And then, The consequences of that flip cascaded forward through billions of years. The slow, retrograde rotation means a weak Coriolis effect. The Coriolis effect is the deflection of moving fluids caused by the planet's rotation. On Earth, it organizes weather systems. It causes hurricanes to rotate. It creates the trade winds, the westerlies, the polar jet streams. It drives organized meridional circulation that transports heat from the equator toward the poles. On Venus, the slow rotation means weak Coriolis forcing. Without it, the atmosphere can't develop the same kind of organized heat redistribution. The heat from the sun just builds up uniformly. The slow rotation also connects directly to Venus's lack of a significant magnetic field. Earth's magnetic field is generated by the geodynamo, the movement of liquid iron in Earth's outer core, organized into specific convection patterns by the Coriolis effect from Earth's rotation. Earth spins once every 24 hours, fast enough to drive organized convection in the liquid iron core, fast enough to generate a sustained global magnetic field. Venus spins once every 243 Earth days, almost certainly too slow to drive an effective geodynamo. Even if Venus has a liquid iron outer core similar to Earth's, the rotation rate is probably insufficient to organize the convection into the pattern needed for a strong, sustained magnetic field. The result is that Venus has almost no intrinsic magnetic field, essentially negligible. This matters enormously. Earth's magnetic field creates the magnetosphere, a magnetic bubble extending tens of thousands of miles into space around the planet. The solar wind, the constant stream of charged particles flowing outward from the sun at hundreds of miles per second, is deflected by this bubble. Most of the solar wind flows around the planet without ever reaching the atmosphere. The atmosphere is shielded, protected. On Venus, without a magnetosphere, the solar wind interacts directly with the upper atmosphere. An induced magnetosphere forms in the ionosphere, the electrically charged upper atmospheric layer, providing some protection. But it's significantly less effective than Earth's intrinsic field. Over billions of years, the solar wind has been stripping lighter atoms from Venus's upper atmosphere, hydrogen particularly. In the upper atmosphere, above most of the atmospheric mass, individual hydrogen atoms can reach escape velocity when energized by the solar wind interaction. Hydrogen is the lightest element. It escapes most easily, and every water molecule that gets photodissociated in the upper atmosphere releases hydrogen atoms. Those hydrogen atoms, already in the upper atmosphere, are vulnerable. Over billions of years, one hydrogen atom at a time, an ocean's worth of hydrogen has escaped into interplanetary space, carried away by the solar wind. The oxygen left behind from the destroyed water combined with surface rocks. The water was gone. One ancient impact that reversed a planet's spin. And, from that single event, a chain of consequences. Slow rotation created weak magnetic field. Weak magnetic field failed to protect against solar wind. Solar wind stripped hydrogen from the atmosphere. Hydrogen loss destroyed the water. Destroyed water ended the geological carbon thermostat. Ended thermostat allowed CO2 to accumulate unimpeded. CO2 accumulation built the greenhouse effect. Greenhouse warming drove the runaway feedback loop. Runaway feedback completed the destruction of all remaining water. And the end state is what we call Venus today. One impact, one reversal of spin, 4.5 billion years of consequences. The surface of Venus, as revealed by radar mapping and the Venera surface missions, has a specific geological character. Volcanic plains cover roughly 80% of the surface, vast, relatively flat lowlands formed by massive outpourings of basaltic lava. These plains look like Earth's ocean floors in composition, but they're not underwater. They're dry, blazing hot, and they haven't seen water in an unimaginably long time. The highland regions, Ishtar Terra and Aphrodite Terra, being the major ones, rise significantly above the plains. Ishtar Terra, in the north, is home to the Maxwell Montes mountain range, Venus's highest terrain. The peaks of Maxwell Montes reach about 7 miles above the surrounding lowlands, slightly higher than Mount Everest above Earth's sea level. The metallic frost observed at the highest elevations, possibly tellurium compounds or iron pyrite, is unique to Venus. At lower altitudes, the temperature is too high for these compounds to condense. At the peaks, it's just cool enough. So the highest points on Venus are dusted in something metallic rather than something icy. The coronae structures, roughly circular, crown-like geological features with raised rims and interior depressions, appear throughout the surface. About 500 are known, ranging from a few tens of miles to over 1,000 miles in diameter. They form where hot mantle material pushes up from below, creating a dome, which then subsides as the mantle material spreads outward, leaving behind the ring structure. Coronae are distinctly Venian. We don't have anything quite like them on Earth, because Earth's plate tectonics efficiently distributes internal heat in ways that prevent the kinds of localized mantle upwellings that produce coronae. Venus, with its stagnant lid and internally building heat, produces them instead. The tesserae remain the most scientifically compelling terrain on Venus. Their ancient, heavily deformed appearance, their position at higher elevations than the volcanic plains, their chemical composition unknown in detail from orbit, all make them a primary target. If ancient oceans existed on Venus, their sediments might be preserved in tesserae. If minerals, formed in the presence of liquid water, are present in tesserae terrain, that's direct evidence of an aqueous past. NASA's Da Vinci mission, currently in development, is designed specifically to target the Alpha Regio Tessera region during its descent. A spherical probe will plunge through Venus's atmosphere, measuring chemistry at every altitude, and in the final minutes before impact, its cameras will photograph Alpha Regio at higher resolution than any previous mission. If those images show sedimentary layering, if they show minerals that require water to form, if they show evidence of an ancient shoreline or river channel, that would be one of the most important discoveries in planetary science history. We'd know, for the first time, that Venus once had oceans, that it was once genuinely habitable, that the runaway greenhouse didn't just theoretically happen at some nebulously defined point in the past, it happened to a world that was previously alive with liquid water. And that changes the entire story of Venus from a cautionary tale to something even more poignant. The possibility of life in Venus's cloud layers has generated genuine scientific discussion and one major controversy. High in Venus's atmosphere, at about 37 to 43 miles altitude, temperatures and pressures fall within ranges where some of Earth's most hardy microorganisms can function. Temperatures in this zone range from about 150 to 180 degrees Fahrenheit, or about 66 to 82 degrees Celsius. Still hot. above the tolerance of most organisms on Earth. But some extremophile bacteria survive briefly at temperatures up to about 275 degrees Fahrenheit, or 135 degrees Celsius. The pressure at these altitudes is close to 1 Earth atmosphere. The gravity is similar to Earth's. If there were microorganisms riding Venus's upper cloud layers, they'd need to survive in concentrated sulfuric acid aerosols at high temperatures under continuous ultraviolet bombardment. The kind of biochemistry that could do that would have to be radically different from anything we know on Earth. But the question remained interesting enough that it attracted serious attention. In September of 2020, a research team announced a detection of phosphine in Venus's atmosphere using radio telescope observations. Phosphine, one phosphorus atom bonded to 3 hydrogen atoms, is produced on Earth by biological processes in anaerobic environments and by some industrial chemistry. In rocky planet atmospheres with oxygen, it has no known efficient non-biological source. If it was genuinely present, it was hard to explain without invoking biology. The announcement generated immediate, intense scientific interest and equally immediate skepticism. In the months and years that followed, multiple teams reanalyzed the same telescope data. The consensus that emerged was that the original signal was weaker than reported and likely arose from instrumental artifacts or data processing issues. Additionally, the chemical environment of Venus's clouds makes phosphine extremely unstable. The acid would destroy it rapidly, so any biological source would have to be continuously producing it at very high rates to maintain even the concentrations originally claimed. The current state of the science is that the phosphine detection is not confirmed. Most researchers regard the original signal as not being genuine phosphine. This doesn't mean life in Venus's clouds is ruled out. It just means we don't have evidence for it. What the episode demonstrated is how much we need dedicated missions to Venus with proper atmospheric chemistry instruments, rather than relying on Earth-based telescope observations with their inherent limitations. The upcoming Da Vinci mission will carry an atmospheric chemistry instrument called VASI, the Venus Atmospheric Structure Investigation, that will make detailed chemical measurements during descent. If phosphine is present in detectable amounts, VASI should find it. If it's not, that will settle the question for the altitude range Da Vinci samples. The biological possibility remains open. But open means unconfirmed, not confirmed. The distinction matters. The 3 missions, now in development, represent the most ambitious return to Venus in decades. NASA's Da Vinci Deep Atmosphere, Venus investigation of noble gases, chemistry, and imaging is primarily an atmospheric probe mission. A spherical descent sphere, about 3 feet in diameter, will plunge through Venus's atmosphere over about an hour of descent, measuring the chemistry at each altitude level. The noble gas measurements are particularly important. Noble gases, helium, neon, argon, krypton, xenon, are chemically inert. They don't react with other atmospheric constituents. They don't get removed by weathering or biology. The isotopic ratios of noble gases in a planet's atmosphere are a kind of chemical fingerprint of the planet's geological and atmospheric history. Comparing Venus's noble gas isotopic ratios to Earth's and to meteorite samples will constrain when and how Venus's atmosphere evolved. Did Venus start with a water-rich atmosphere like Earth's? When did the volatile inventory change dramatically? What was the ancient atmospheric composition before the runaway greenhouse? Noble gases can help answer these questions in ways that other measurements cannot. Da Vinci also carries the CubeSat infrared atmospheric spectroscopy instrument, intended to study Venus's atmosphere from orbit before the descent probe releases. NASA's Veritas Venus, emissivity, radio science, INSAR, topography, and spectroscopy is an orbital mission that will map Venus's surface at dramatically higher resolution than Magellan's 30-year-old maps. Veritas will use a synthetic aperture radar to produce topographic maps with roughly 100-meter resolution, roughly 3 times better than Magellan's best. It will look for evidence of current geological activity, deformation, recent volcanism, heat signatures. It will also carry an infrared spectrometer to detect mineralogy at the surface, what types of rocks are present, whether there are carbonate minerals that would indicate past aqueous chemistry. Veritas was placed on hold in 2023 due to budget issues at NASA, but is scheduled to proceed. The European Space Agency's Envision mission rounds out the fleet. Envision is an orbital mission combining a synthetic aperture radar, atmospheric chemistry instruments, and subsurface sounding radar that can look beneath Venus's surface. The 3 missions, Da Vinci, Veritas, and Envision, are designed to work somewhat in concert, building a comprehensive picture of Venus that we've never had. Together, they represent humanity's most serious attempt to understand why our nearest planetary neighbor became what it is, and by extension, what it means for the habitability of rocky planets everywhere. Venus matters for the search for life beyond our solar system in a way that goes beyond the planet itself. The James Webb Space Telescope is capable of detecting the atmospheres of rocky exoplanets around nearby stars. When a planet passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. The atmosphere imprints its chemical signature on that light. By analyzing the light, scientists can determine what gases are present in the exoplanet's atmosphere. For the first time in history, we can study the chemistry of atmospheres on planets around other stars. And some of the first rocky planets being targeted for this kind of atmospheric study are planets orbiting the TRAPPIST, one system, a nearby small red dwarf star with 7 rocky planets, at least 3 of which are in or near the habitable zone. The question of whether any TRAPPIST, 1 planets have atmospheres, let alone habitable atmospheres, is actively being investigated with Webb right now. But to interpret what Webb sees, we need reference points. We need to know what a habitable rocky planet's atmosphere looks like. And we need to know what an uninhabitable rocky planet's atmosphere looks like. Earth provides the first data point. Venus provides the second. A thick CO2 atmosphere with sulfuric acid clouds and no water vapor absorption features would look, spectroscopically, like Venus. That would be a warning sign. A Venus analog around another star. A world that might look Earth-like in a telescope catalogue, but is, in reality, a 900-degree furnace. Without Venus as a data point, we'd have trouble knowing how to interpret those signatures. With Venus studied carefully, with its atmospheric composition and climate history understood in detail, we can build better spectroscopic templates. Templates for what a runaway greenhouse world looks like from outside. This is one of the reasons the planetary science community has been pushing hard for renewed Venus exploration. Not just for Venus's sake. For the sake of every rocky planet we're going to study around other stars. Venus is the calibration point for the worst outcome. The point where habitability ends and hell world begins. Understanding exactly where that line is and what atmospheric signatures mark it is fundamental to astrobiology at interstellar distances. One aspect of Venus's history that's worth dwelling on is the absence of a moon. Earth has the moon. Mars has two small moons, Phobos and Deimos, but they're captured asteroids, not large moons. Mercury has no moon. Venus has no moon. Earth's moon is the largest in the solar system relative to its host planet. Its mass is about 1% of Earth's. That's unusually large. It's believed to have formed from the debris of the giant impact that struck early Earth, the same kind of giant impact that may have reversed Venus's rotation. The moon's gravitational influence on Earth is stabilizing. Earth's axial tilt, the angle between its rotation axis and its orbital plane, is about 23.5 degrees. This tilt has varied only between about 22.5 and 24.5 degrees over the past few 100 million years. The moon holds it steady, without the moon's gravitational stabilization. Computer simulations suggest Earth's axial tilt could swing chaotically between near zero and as much as 85 degrees over geological timescales driven by gravitational resonances with the other planets. A chaotically varying axial tilt would produce chaotically varying climates. Near zero tilt would minimize the seasons, concentrating permanent heat at the equator and permanent cold at the poles. Very high tilt would produce extreme seasons, each hemisphere spending months in continuous sunlight, then months in continuous darkness. Cycles of extreme variations in tilt would stress any biosphere trying to adapt to the changing conditions. On geological timescales, this would likely prevent the development of complex life. Venus has no moon. Its axial tilt, 177 degrees, essentially inverted due to the retrograde. Rotation has almost certainly varied, chaotically, over Venus's history without a large moon to stabilize it. Whether that axial instability contributed to Venus's climate becoming unstable and crossing into the runaway greenhouse is genuinely debated. We don't know the answer. But every factor that distinguishes Earth from Venus adds up. The moon is one of those factors. Another asymmetry between two planets that seem almost identical in their basic statistics. Think about what Venus represents when you take in the full picture. It's our nearest planetary neighbor for most of its orbital cycle. At its closest approach to Earth, its inferior conjunction Venus comes within about 25 million miles. No other planet gets that close. Light takes about 2 minutes to cross that gap. In cosmic terms, it's next door, and it's the most hostile surface in the solar system. Not the most distant, not the most exotic, the most hostile, sitting 25 million miles away at its closest, glowing in our evening sky named for beauty. A surface that has destroyed every machine we've ever sent to it within hours. A temperature that melts common metals. A pressure that would instantly destroy any unprotected object. Sulfuric acid clouds that attacked every probe on the way down. Super-rotating winds of 200 miles per hour in the upper atmosphere. An atmosphere 96%, CO2 at 92 atmospheres. No liquid water anywhere. No functional magnetic field. No large moon. No geological thermostat. No reset. No way back from what it has become. This is Venus, our neighbor, the one named for love. A planet that has been cooking in its own atmosphere for hundreds of millions of years with no sign of stopping. There's a question embedded in all of this that deserves a direct answer. Could what happened to Venus happen to Earth? Not in any time frame relevant to our civilization. Not in the next million years. Probably not in the next billion years. But eventually, possibly. The sun is getting brighter. Slowly, about 10% brighter every billion years. In approximately 1 billion to 1.5 billion years from now, solar models suggest that Earth will begin to experience conditions where the runaway greenhouse threshold becomes a real concern. The precise timing depends on carbon cycle feedbacks, on how Earth's climate adjusts, on factors that are difficult to model this far out. But the basic physics is the same physics that ran on Venus. The same mechanism. The same feedback loop. Earth got more time than Venus because Earth started at a safer distance from the Sun, with a stronger magnetic field, with a large stabilizing moon, with active plate tectonics driving the carbon thermostat. All of those factors bought time. They didn't change the fundamental outcome of a brightening sun, eventually providing too much energy for a water-covered world to stay below the runaway greenhouse threshold. In something between 1 and 2 billion years, the models suggest the runaway greenhouse will come for Earth. Everything that makes Earth habitable will eventually be undone by the same process that undid Venus just later. On any human timescale, this is irrelevant. A billion years from now is 4 times the current age of complex multicellular life on Earth. It's 100 million times the length of recorded human history. Whatever humanity does between now and then, whether we survive, whether we become something unrecognizable, whether we've long since left Earth for other worlds, is impossible to predict. But the physics is real. The mechanism is the same mechanism that already claimed Venus. And sitting with that knowledge that Earth's habitability has an expiration date written in the same equations as Venus's fate changes how you look at our own planet. Not with fear, with appreciation. We are in the window. Right now, in the narrow, specific, improbable window where the sun is bright enough to keep water liquid but not bright enough to trigger the runaway, where the magnetic field is strong enough to protect the atmosphere, where the moon is large enough to stabilize the tilt, where the plate tectonics are active enough to run the carbon thermostat, where all of it works. Right now, Venus is a reminder that the window isn't infinite. Earth is a reminder that inside the window, life does what it does. Complex, diverse, persistent, creative life. Filling every available niche, changing the chemistry of the atmosphere, shaping the landscape, building things that eventually look up at the planet, named for beauty, and try to understand what happened to it. Now, there's a concept that comes up repeatedly in discussions about Venus that deserves its own focused treatment. The inner edge of the habitable zone. The habitable zone is defined as the range of distances from a star where a rocky planet could maintain liquid water on its surface. Not too hot, not too cold. The Goldilocks band. The outer edge is set by conditions where a planet gets so little stellar energy that CO2, the last efficient greenhouse gas, freezes out of the atmosphere. The greenhouse effect collapses, and the planet freezes entirely. The inner edge is set by the runaway greenhouse threshold, the point where solar energy input is high enough to trigger the feedback loop that destroyed Venus. These boundaries aren't precise lines. They're gradients, zones of uncertainty, where conditions become increasingly marginal as you approach them. And the inner edge is more uncertain than most textbook treatments acknowledge. Different climate models place the inner edge at different distances from a sun-like star. Some models suggest the inner edge is at about 0.95 astronomical units, just inside Earth's orbit. Other models, incorporating different atmospheric physics and cloud feedback mechanisms, place it at 0.9 astronomical units, or even closer. 1 astronomical unit is Earth's average distance from the Sun, about 93 million miles. Venus orbits at about 0.72 astronomical units. Whether Venus was ever genuinely inside the habitable zone is part of that uncertainty. And the difference matters enormously for how we classify exoplanets. When exoplanet surveys catalog rocky worlds around other stars and classify them as potentially habitable, those classifications are based on the habitable zone boundaries. If the inner edge of the habitable zone is incorrectly placed, if we've been drawing the line too close to the star, then some planets we've been calling potentially habitable are actually Venus analogues. Worlds past the point of no return, looking Earth-like in our catalogues, hosting a 900-degree furnace underneath their clouds. This is one of the most urgent reasons to understand Venus better. The calibration of the inner edge is one of the most important numbers in astrobiology. It determines how many potentially habitable worlds there are in the galaxy. It determines which planets are worth pointing our best telescopes at. It determines our estimates of how common life might be. Getting that number right requires understanding what happened on Venus in enough physical and chemical detail to build accurate climate models. We don't have that understanding yet. The upcoming missions Da Vinci, Veritas, Envision will significantly improve it. But right now, the inner edge of the habitable zone has real uncertainty, and Venus is the reason that uncertainty matters. The history of our understanding of Venus is also a history of how profoundly wrong science can be when working with limited data. Before space exploration began in the early 1960s, scientific understanding of Venus was based entirely on observations made from Earth. Those observations were limited. The cloud layers prevented any view of the surface. The atmosphere was opaque to visible light from below the clouds. Astronomers could measure Venus's size, its orbital period, its distance from the Sun, and some properties of its upper atmosphere. They could not see the surface at all. So they filled in the blank with models and speculation. Some models suggested Venus might be a tropical world, warm, humid, covered in swamps and ancient vegetation. The reasoning went something like this: Venus is closer to the Sun than Earth, so it's warmer. But if it were much hotter than Earth, the water would have evaporated. The thick clouds might be water vapor, the same way Earth sometimes has thick cloud cover. Under those water vapor clouds, the surface might be like a perpetual, planet-wide tropics, hot and wet. Some proposals went further, suggesting the clouds might be hiding an ocean world, a planet entirely covered in warm oceans, with no land visible under the clouds. Others proposed that Venus might be like Earth during the age of ancient forests, a younger seeming version of our own world, perhaps in an earlier geological stage. Some scientists who were more cautious noted that the greenhouse effect from Venus's likely carbon dioxide atmosphere might make the surface extremely hot. Carl Sagan's 1960 paper explicitly predicted that the greenhouse effect could explain very high Venus surface temperatures. He was right. But at the time, the consensus hadn't yet formed around that conclusion. There were competing models. Uncertainty was genuine. The Mariner 2 spacecraft settled the question definitively in December of 1962. Mariner 2 flew past Venus and measured its surface temperature using microwave and infrared radiometers. The readings came back unambiguous. The surface was around 800 degrees Fahrenheit, or 427 degrees Celsius, possibly hotter. The specific numbers were revised by later missions, but the essential finding was immediate and clear. Venus was searingly, lethally hot. Not a tropical paradise. Not an ocean world. Not a younger Earth. A furnace. In one flyby, in about 42 minutes of atmospheric observation, Venus went from a world of speculative possibilities to a confirmed hostile environment. The mystery was solved. The romantic image was gone. What remained was just the science. And the science said, 900 degrees, 92 atmospheres, sulfuric acid. In retrospect, the error in the pre-space age models is understandable. We had almost no data. The models were doing their best with what was available. But the lesson is important. When you can't see inside something, your models of what's inside can be completely wrong, not slightly off. Completely wrong. From a tropical paradise to a planet that destroys spacecraft in 2 hours. That's the range of the error. And the lesson applies directly to how we should think about exoplanets today. We have limited data on exoplanet atmospheres. Our models are doing their best with what's available. But until we actually measure the surface conditions, or at least get detailed enough atmospheric chemistry data to constrain them strongly, our classifications of exoplanets as potentially habitable carry the same kind of uncertainty as the pre-Mariner 2 view of Venus. The universe is patient about revealing how wrong our assumptions were. The spacecraft usually deliver the news. There's a comparison that's worth making carefully. Mars gets far more attention as a potential destination for human exploration. And there are good reasons for that. Mars is cold. Very cold. Average surface temperature around -80 degrees Fahrenheit or -62 degrees Celsius. Thin atmosphere, about 1% of Earth's pressure. Weak gravity, about 38% of Earth's. Radiation exposure from the lack of a global magnetic field. Dust storms that cover the planet periodically. No liquid water on the surface. Mars is genuinely difficult to survive on. Any human settlement on Mars would require pressurized habitats, radiation shielding, food production, water recycling, and constant technical support. But we have proposals for all of that. Serious, detailed engineering proposals. Habitat designs, life support systems, radiation shielding strategies, resource extraction plans. Humans could, with sufficient technology and resources, survive on Mars. Not easily. Not safely, without enormous preparation. But physically, it's achievable. The challenges are engineering challenges. They're problems with solutions. Venus is not like that. On Mars, the primary killers are the thin atmosphere, the radiation, and the cold. All three can be addressed by enclosure, a pressurized, shielded habitat. You go inside. The habitat protects you. You survive. On Venus, you can't just go inside a habitat. The habitat itself will be destroyed. The external pressure requires the habitat to be a pressure vessel rated to 92 atmospheres, comparable to a deep-sea submarine, but needing to operate while sitting in 900-degree heat. The temperature requires continuous active cooling, removing enormous amounts of heat from the interior continuously, forever. Any gap in the cooling fails. Any structural failure of the pressure vessel fails. Any failure of power, which runs the cooling, fails. All of these failure modes are immediate and total, not gradual situations where you have time to respond. Instant. On Mars, life support failures are serious, but often give you time. A suit leak might give you minutes. A habitat breach might give you time to patch it. Systems can fail in ways that allow responses. On Venus's surface, essentially all failure modes are immediate and total. The environment overwhelms everything before any response is possible. This is why nobody has a serious proposal for a crewed surface mission to Venus. Not because we've given up, because the physics of the surface don't accommodate the kind of engineering responses that keep humans alive in other extreme environments. The only proposal for human presence near Venus that makes some engineering sense is the aerial concept. A pressurized airship floating at high altitude in the relatively temperate zone of the cloud. Tops. Still extremely challenging. Still facing the acid chemistry and the winds and the temperature. But at least the pressure and temperature at those altitudes are within ranges where maintained habitation is theoretically conceivable. The surface, though, remains beyond reach. Not just beyond our current technology. Beyond any technology we can currently conceptualize building with known materials. One of the less discussed aspects of Venus is how it affected the early development of planetary science as a discipline. Before the space age, planetary science was largely observational, astronomy measuring properties of planets from a distance. Masses, orbits, sizes, albedos, and whatever spectroscopic information could be gathered from Earth. The field was respected, but somewhat peripheral. The planets were seen primarily as objects to be charted, not as worlds to be understood. The Venera missions, and the Mariner 2 flyby before them, changed this. They demonstrated that planets are real places with specific physical conditions that can be measured directly. That models built from Earth-based observations can be profoundly wrong. That understanding another world requires going there. Actually sending instruments through the atmosphere. Actually measuring the surface. Actually testing predictions against reality. The Venera program made planetary science into what it is today, an empirical discipline where theories are tested against in-situ measurements, where ground truth means actually going to the ground. The engineers and scientists who designed the Venera probes were doing something that had never been done, building machines to survive in an environment no human could survive in, an environment that couldn't be replicated on Earth. An environment whose properties could only be inferred from distant observations before the probes actually arrived. They got important things wrong in the early missions because their models of Venus were wrong, and each failure taught them something. Venera 4 taught them the surface pressure was far higher than expected. Venera 5 and 6 confirmed the new pressure estimates. Venera 7 showed they'd finally built something strong enough. Venera 8 told them there was light at the surface. Venera 9 and 10 told them what the surface looked like. Venera 13 told them what the surface chemistry was. 20 years of incremental learning. 20 years of building on failure. The Venera program is one of the great engineering achievements of the 20th century, and it's significantly underappreciated compared to the Apollo program or the Mars rover missions. Partly, this is because the Soviet program was less publicly documented than NASA's. Partly it's because we sent probes that survived for 2 hours, sounds less impressive than we landed humans, and they came back safely. But the difficulty of Venera's target, compared to the Moon or Mars, makes the achievement remarkable. No mission to any other body in the solar system has faced an environment as immediately and thoroughly hostile as Venus's surface. The fact that any of those probes survived long enough to transmit data at all is a testament to how good Soviet planetary engineers were. The timing of Venus's transformation, when exactly the runaway greenhouse began, is one of the questions Da Vinci and Veritas are designed to help answer. The answer matters for astrobiology because it determines how long the inner habitable zone boundary has been where it currently is for our Sun. If Venus was habitable until relatively recently, say, within the last billion years, that has different implications than if Venus was never truly habitable at all. 1 billion years of habitability on Venus would mean the inner habitable zone was significantly closer to the Sun than it currently is, for a significant fraction of the solar system's history. That would mean more planets in more star systems spend more time in the habitable zone, more opportunities for life. If Venus was marginal from the beginning and crossed into the runaway regime very early, that suggests the inner edge has always been near where it currently is, and Venus orbit distance planets are consistently bad news. The noble gas measurements from Da Vinci are the key to this. The argon-36 to argon-38 isotopic ratio and similar ratios for other noble gases will reveal the timing and rate of Venus's atmospheric evolution. Combined with the mineralogical measurements from Veritas, looking at whether Venus's oldest terrain contains water-formed minerals, the picture should become significantly clearer. We may know within the next decade whether Venus was ever a world like Earth, whether the runaway greenhouse happened early or late, whether the window of habitability was wide or narrow. And that will tell us something profound about the prevalence of habitable worlds in our galaxy. There's one more dimension to Venus's story that we haven't fully explored yet. The question of what Venus's clouds actually look like, not from outside the planet, not from below in the orange haze, but from within them. If you were inside Venus's cloud deck, at the altitude where the temperature and pressure are closest to Earth-like, what would you see? You'd be surrounded by a dense, yellowish haze. The individual cloud droplets are tiny, a few microns across, thousands of times smaller than a raindrop on Earth. Visibility would be limited, similar to a thick fog on Earth. You might see a few hundred meters ahead, maybe less in the denser regions of the cloud layer. Everything would be faintly yellow, tinged by the sulfuric acid droplets and whatever other chemicals are present. The light would be diffuse, coming from no particular direction, because the cloud layer is being illuminated from above by sunlight scattering through the acid aerosols. There's no clear sky above you in this zone. No blue. No stars visible. No sun visible. Just an omnidirectional yellowish glow in the acid mist. Below you, the cloud layer gets thicker and darker as you descend. The temperature increases. The pressure increases. The acid concentration of the droplets changes. Above you, the cloud layer thins. The upper boundary is at about 40 to 43 miles altitude. Above that, there are high-altitude haze layers of sulfuric acid particles, and eventually the sky clears somewhat into a genuine upper atmosphere. From the upper cloud boundary looking upward, you could probably see the sun as a distinct, if slightly blurred, disk far brighter than it appears from Earth's surface. And the sky at that altitude would be dark enough at the edges that stars might be visible. The upper atmosphere of Venus is being illuminated directly by the sun. Below you, however, is a world that no spacecraft has photographed from within the clouds themselves. The Vega balloon probes in 1985 were the first instruments to actually float within Venus's cloud layer. They transmitted data for about 46 hours before their batteries ran out. They measured wind speeds, temperatures, pressure, light levels, and detected turbulence and convective upwellings. The cloud layer was found to be dynamic, not a uniform, calm blanket, but an active zone with vertical motions, convective cells, and turbulent regions. The kind of dynamic atmosphere you'd expect given the temperature gradient between the hot surface below and the cold upper atmosphere above, driving convection. The images and data from the Vega probes don't show you what you'd see inside the clouds with human eyes. The instruments were measuring things human eyes couldn't detect directly, but the picture they built of a turbulent, chemically complex, dynamically active cloud layer is far more interesting than the simple image of uniform, overcast skies. Venus's clouds are alive with physics. Convective cells rising and falling. Winds of over 200 miles per hour circling the planet at cloud-top altitude. Acid droplets forming and falling and evaporating in the cycles that maintain the cloud system. A chemical factory running continuously, turning volcanic sulfur into sulfuric acid and back again. This is what's hiding behind that smooth, luminous, featureless exterior. Not calm, not peaceful. Violent, dynamic, and chemically hostile at every level. The way Venus's atmosphere interacts with the sun is also unusual and worth understanding. Because Venus is closer to the sun than Earth, the solar irradiance at Venus's distance is about 1.9 times higher than at Earth's distance. More energy per square meter arriving from the sun. But Venus reflects so much of that energy back into space, 65%, that the actual amount of solar energy absorbed by Venus is similar to or slightly less than Earth's. Earth reflects about 30% and absorbs the rest. Venus reflects 65% and absorbs 35%. 1.9 times more solar energy arrives at Venus. But Venus reflects more than twice as large a fraction. The numbers nearly cancel. The absorbed solar power at Venus is roughly comparable to Earth's. And yet Venus is 900 degrees instead of Earth's average of 59 degrees. The difference is entirely the greenhouse effect, not more solar input, more heat retention, more energy being trapped in the lower atmosphere and not being allowed to radiate back to space. This is a profound point. Venus doesn't bake primarily because it's close to the sun. Venus bakes because it can't release heat. The energy budget is nearly Earth-like. The atmospheric response is completely different. The same amount of energy in and almost none of it out. The 96% carbon dioxide atmosphere is so efficient at trapping infrared that the surface temperature had to rise all the way to 900 degrees before enough heat was finally escaping through the dense atmosphere to balance the incoming solar energy. 900 degrees is the equilibrium temperature for a planet with Venus's atmospheric composition and pressure. Not because 900 degrees is a special number, because that's where the incoming and outgoing energy finally match for an atmosphere that thick and CO2 rich. This is why Venus is the clearest example of what an extreme greenhouse effect looks like. Not because it gets more solar energy than Earth. It doesn't, when you account for the reflectivity. But because it traps what it gets so completely. The oxygen in Venus's atmosphere is another piece of the story that rarely gets attention. Venus's atmosphere is about 96% CO2, nearly 4% nitrogen, and trace amounts of other gases. One of those trace gases is molecular oxygen, O2, present at about 20 parts per million. For comparison, Earth's atmosphere is about 21% O2. Venus has about 10,000 times less oxygen in its atmosphere than Earth does. On Earth, the presence of free oxygen, oxygen that isn't bound up in other molecules, is a signature of biology. Photosynthesis produces oxygen. Without continuous biological production of oxygen, it would quickly react with surface rocks and organic compounds and disappear. The oxygen in Venus's atmosphere is thought to come primarily from the photodissociation of CO2 by ultraviolet radiation, the same process that breaks water molecules in the upper atmosphere. Also breaks CO2 molecules, releasing atomic oxygen that recombines into O2. It's a purely chemical, non-biological process. And the fact that it produces only 20 parts per million rather than 21% tells you something about the balance of production and consumption. Venus's oxygen is quickly consumed by reactions with surface minerals and volcanic gases. It doesn't build up. On Earth, the biological production of oxygen completely overwhelmed the consumption processes and built up to 21% over a couple of billion years. On Venus, there's no biology. No oxygen production beyond the small photochemical amount, and what little there is gets quickly consumed. The trace oxygen in Venus's atmosphere is not a biosignature. It's a photochemical byproduct. But it's a reminder that Venus's atmosphere is chemically active. Things are reacting. Molecules are being broken apart and reformed. The whole atmospheric chemistry of Venus is a complex set of interconnected cycles: the sulfur cycle, powering the acid clouds, the carbon cycle that can no longer regulate CO2, the nitrogen chemistry that maintains the background atmospheric composition. Understanding all of those cycles in detail is one of the scientific goals of the upcoming missions. Because those cycles on Venus, understood properly, help us understand similar cycles on other planets, in other conditions, around other stars. There's one more physical process operating on Venus that deserves mention before we close: atmospheric escape. The process by which Venus is slowly, continuously losing its atmosphere to space. Every planetary atmosphere is in a state of slow loss. Lighter molecules at the top of the atmosphere have a distribution of speeds. Some are moving fast enough to exceed the planet's escape velocity. Those molecules fly off into space, never to return. This process is called Jean's escape, after the physicist who first calculated it quantitatively. On Earth, Jean's escape is extremely slow for most gases. Oxygen, nitrogen, CO2. They're heavy enough that very few molecules are moving at escape velocity at any given moment. Over the age of the solar system, Earth has lost only small amounts of its atmosphere through Jean's escape. But hydrogen is very light. At the top of Earth's atmosphere, a significant fraction of hydrogen atoms are moving fast enough to escape. Earth loses hydrogen to space continuously. It's partly why Earth's hydrogen is mostly locked up in water rather than floating free as hydrogen gas. Venus loses hydrogen too. And on Venus, the process is enhanced by the lack of a magnetic field. The solar wind interacts directly with Venus's upper atmosphere. It can energize atmospheric particles, giving them extra velocity, enough in some cases to reach escape velocity. This process, called ion escape or non-thermal escape, removes particles from Venus's atmosphere more efficiently than Gene's escape alone. Hydrogen is the primary victim, which is why Venus's deuterium to hydrogen ratio is 150 times higher than Earth's. The hydrogen escaped. The deuterium, being heavier, escaped more slowly. The ratio changed over time as the lighter isotope left faster. The current ratio is a record of billions of years of hydrogen loss. 150 times higher than Earth tells you that most of the hydrogen that was originally in Venus's atmosphere, all the hydrogen that was originally in Venus's water, is gone, scattered into interplanetary space. Long ago, incorporated into the solar wind, and eventually into the outer solar system. The water that may once have filled Venus's oceans is, atom by atom, spread across the inner solar system, gone from the planet it once made blue, leaving behind the orange-lit, acid-clouded, 900-degree world we call Venus today. Here's a final thought about Venus that takes the longest view. In the far future of our solar system, the Sun will eventually exhaust its hydrogen fuel in its core. When that happens in about 5 billion years from now, the Sun will expand into a red giant. Its outer layers will swell to perhaps 100 times the current solar radius. In the final stages, the Sun will likely engulf Mercury and Venus completely, and possibly Earth as well. Everything on the surfaces of those planets will be vaporized. Venus's 900-degree furnace will be engulfed by a stellar envelope that is thousands of degrees hotter. The distinction between Venus's surface temperature and the interior of a star will cease to have meaning. But before that happens, in the billion or 2 billion years between now and Venus being swallowed, something interesting might be occurring in the outer solar system. As the Sun brightens, the habitable zone moves outward. The inner edge moves further from the Sun. The outer edge moves further too. Eventually, Mars's surface might reach temperatures where liquid water could briefly exist. Europa, currently frozen, might melt. Titan, currently cold and hydrocarbon-rich, might see its chemistry become more interesting. The habitable zone doesn't stay fixed. It migrates outward as the star brightens. And right now, in this moment, Earth is in the window. The habitable zone is centered roughly around Earth's orbit. Venus is just outside the inner edge. Mars is just outside the outer edge. And Earth, somehow, through the combination of all the factors we've discussed, through the carbon thermostat and the magnetic field and the moon and the plate tectonics and the water, Earth is right in the middle, right in the sweet spot, right where it needs to be. For now. Venus is there to remind us that the sweet spot has edges, that the edges are real, that crossing them has consequences that are permanent and total, and that we are extraordinarily lucky to be on the inside. Thank you for spending tonight with me, exploring the deadliest planet in our solar system. We covered the surface conditions, 900 degrees Fahrenheit, 92 atmospheres of pressure, and what those numbers mean for any machine or material that encounters them. We covered the Soviet Venera program, 22 years of engineering effort, more than 15 spacecraft, complete redesigns multiple times, and a maximum surface survival time of 127 minutes. We covered the atmosphere layer by layer from the surface's dense, optically distorted environment, through the lower clouds, through the sulfuric acid cloud deck, to the super-rotating 200 miles per hour winds of the cloud tops. We covered how Venus got this way, the ancient impact that reversed its spin, the loss of its magnetic field, the stripping of its hydrogen by the solar wind, the destruction of its oceans, the collapse of the geological carbon thermostat, and the runaway greenhouse that has been running ever since. We covered what it means for the search for life around other stars, for our models of planetary habitability, for the calibration of the inner edge of the habitable zone, and for our understanding of where Earth sits in its own long timeline. Venus isn't just a cautionary tale. It's a complete case study in how a world almost identical to ours can become something unrecognizable through a specific sequence of physics and chemistry that once started, never stops. Same ingredients, same starting point, different position in space by 30 million miles. And everything else followed from that. If this changed how you see that steady, brilliant point of light the next time you spot it on the horizon after sunset, then tonight was worth it. Take a moment to like the video or subscribe if you haven't already. It keeps this channel going. And the next time you see Venus glowing in the evening sky, steady, brilliant, impossibly bright, named for something beautiful, remember what's underneath all that reflected light. 900 degrees, 92 atmospheres, acid clouds, a planet that crossed a line it could never come back from, glowing like something magnificent, completely transformed from whatever it once was. Sleep well tonight, knowing that Earth is still on the right side of that line. For now, for a very long time to come. Good night.